Hope all of you are well. So today we are going to discuss almost we have close to the end, that is the Cauchy's residue theorem and its application. So if you still not have visited the previous video lectures, please visit, because to know this topic you have to understand the previous concepts also. So now let us come forward to the discussion. So in my last video lecture I have already discussed about how to calculate the residues for an analytic function. So the formulas of the residue we just are again trying to recapitulate. So if we are having a pole of order 1, that is a simple pole, then residue at z equals to z0 can be calculated using this formula. Limit z tends to z0, z minus z0 will be multiplied with f of z. Now if you are having a pole of order m, that is more than 1, it can be 2, 3, etc., then the residue at z equals to z0 at that particular point, that is pole of order m, can be calculated using this formula: 1 upon m minus 1 factorial limit z tends to z0 d dz, that is power should be, order of the differentiation will be m minus 1, that is d to the power m minus 1 dz to the power m minus 1, z minus z0 whole to the power m. This will be multiplied with f of z. Now we come to the most important theorem on which this whole topic is lying, that is the Cauchy's residue theorem. And this theorem is having many applications, and this is this makes all the integrations type of problem very simple. So Cauchy's residue theorem says that suppose we are having an analytic function, the fz is analytic, inside a simple closed curve C, except for finitely many singular points z1, z2, zk inside the closed curve C. Then the integral of f of z, the integration should be taken on the anti-clockwise direction of the C. It will be equals to 2 pi I times of the sum of all the residues of f of z at the points z1, z2, zk. So if the analytic function is having some singularities, that is only the finite number of singularities z1, z2, zk. For our instance, we have considered only k number of singularities are there inside C, and then the value of the integration of f of z taken over the closed curve C, that is integration of c f z dz, this value is going to be 2 pi I into sum of all the residues at each and every pole, which is each and every singularities which is going inside the closed curve C, that is summation k equals to 1 up to n residue of f zk. Now to understand this, let us briefly try to understand the concept, how it works. Suppose we are having a closed curve where C is taken in the anti-clockwise direction. It is bound one region, and inside this region the function f of z, inside this region the function f of z is fully analytic. It is analytic, except some finite number of points are there, say z1, z2, z3 dot dot zk, k number of points are there at which the functions is having the singularity. Then how we will be able to find out the answer, or how we will be able to do the integration of f of z over this closed curve C. Now by Cauchy's theorem, what we know that except if we just make those singular points outside of the domain, then the value of the integration of fz along the curve and on the boundary of the curve, the value of the function fz is going to be 0 only, right? So the value of f of z throughout the curve C, along with we have taken small circle surrounding the point z1, z2, zk, but the orientation of the circle I have taken in the clockwise direction. It has this some reason is there behind this, so we have taken in the clockwise direction. Okay, so using the Cauchy's theorem we can write down integration over C fz dz over c1 fz dz dot dot integration over ck f of z dz or cn f of z dz. This value is going to be 0 only. Now if we keep this integration over c f z dz on the left hand side and take all these necessary parts, that is all the rest of the integrations on the right hand side, so these curves will be minus, because all these minus sign I have taken as a plus, and the orientation I have taken in the opposite direction. Here the orientation is taken in the clockwise direction. Whenever I will take all these integrands on the right hand side, so the before the integration the sign should be minus everywhere, right? But that minus sign is adjusted by taking the orientation of the circle in the anti-clockwise direction, because from clockwise to anti-clockwise whenever we will take, the orientation of the circle will become minus C1. So all this minus will get adjusted. Now how to calculate this value? This value we have already calculated from the previous video lecture. I have told you how to calculate the residue, that is b1 equal to 1 by b1 equals to 2 pi I into that part. So we can get the value of this integration as 2 pi I residue at the point z1, 2 pi I into residue at the point c2 z2, and so on. So we are getting the Cauchy's residue formula as 2 pi I into sum of all residues. Now we are going to discuss some of the very important questions from this Cauchy's integral formula to understand the concept. So let us start with the first one. Say it is given in the question that we have to evaluate integration over c z minus 1 upon z plus 1 z minus 2. Whenever such a question will be given to us, first of all we have to find out what are the poles of these functions, what are the singularities of this function. So here you can be able to see that if we make the denominator equals to 0, that is z plus 1 equals to 0, we have z equal to minus 1, and making z minus 2 equals to 0, we are having z equal to plus 2. So z equal to minus 1 and z equal to plus 2, both are the simple poles. Why we are say these are the simple poles? Because the power of these two terms, these two factors, are exactly equals to 1. Now it is given that over a circle we have to do the integration, and the circle is given as mod of z minus I equal to 2. So from this image you will be able to see that here I is located on the imaginary axis, because this is our imaginary axis and this is our real axis. So from this point I we have to go to 2 radius, because 2 steps we have to go forward and 2 steps we have to go downside. So it will go up to plus 3I, and in the negative side of the imaginary axis it will go up to minus I. Now how we will be able to understand that these 2 points, because z equal to minus 1 and z equal to plus 2, these 2 points are the real points, these are not the imaginary points. So how we will be able to understand that these 2 points lie inside or outside the circle? Definitely z equal to 1 lies inside the circle, but how to understand z equal to 2, whether it is inside or outside the circle? We have to take the distance between this center and this point 2, that is mod of 2 minus I. So mod of 2 minus I, if we just calculate, you know that how to calculate the mod of x plus iy. So this can be calculated using root over of x square plus y square. So using this formula I have taken root over of 2 square plus 1 square, because coefficient of I is minus 1, so minus 1 whole square, so it will become plus 1. So the value is going to be root 5. Root 5 is definitely more than 2, but the distance of this radius is maximum 2, but it is going little bit outside, right? So because this point from I is having the distance 2 point something, but the radius of this circle is only 2, so definitely it will end little bit before 2. So 2 will be outside of the circle. So since 2 is outside of the circle, we will not be entertained to find out the residue at the point z equal to 2. Only at z equal to minus 1 we are going to calculate the residue. Since z equal to minus 1 is the simple pole of this function, so residue can be calculated using the formula number 1 of the residues at simple pole. So limit z tends to minus 1, z minus of minus 1, the structure is z minus z0 into f of z. So here z0 is minus 1, so z minus of minus 1 into f of z. So f of z we have substituted here, z minus 1 are going to cancel down from here, and we have to substitute z equal to minus 1. After substituting we are getting the value of the residue is equals to 2 by 3. Therefore the value of the integration will become 2 pi I, as per the formula 2 pi I into sum of all the residues. Since we are having only one residue, that is 2 by 3, so 2 pi I multiplied with 2 by 3, so answer is 4 pi I by 3. Now let us come to the next question. Here we have to find out the value of the integration z square plus 2z plus 1. So basically it is z plus 1 whole square divided by z square, z minus 1, z minus 2. So if we think about the denominator part, then how it is becoming 0 if we put z equals to 0, if we put z equal to 1, and if we put z equal to 2. So these are the three poles of this integration. Or the function f of z. So z equals to 0 is a pole of order 2. Why we say it is a pole of order 2? Because the power of z equals to 2 itself. Now z equal to 1 is a simple pole, it is a pole of order 1. Z equal to 2 is another simple pole, it is a pole of order 1. Now we are having the circle, that is mod z equal to 6. So mod z equal to 6, now you are habituated with this. So mod z means a center at a point 0, because the structure is mod of z minus, I have already told you from the very first video lecture that the circle we are denoting by this mod of z minus z0 equals to r. Z0 will represent the center and r is represent the radius. So here mod of z minus 0, so center is at the point 0 and 6 is the radius, so it will go up to plus 6 this side, it will go up to minus 6 this side. With this the full circle will be created. Now in this circle, within this circle, all these 3 points actually lie: z equal to 0, z equal to 1 and z equal to 2. So all the 3 points, but before this since the 2 poles are simple poles, so we calculate the residue of f at the pole z equal to 1 and z equal to 2 using the simple pole formula, that is limit z tends to 1, z minus 1 multiplied with the whole function f of z. So z minus 1, z minus 1 are going to cancelled out, so we are having limit z tends to 1, the remaining part, so the limit will give us the value of the residue, that is equals to minus 4. Similarly, for the residue of f at z equal to 2, that is also can be calculated by taking limit z tends to 2, z minus 2 multiplied with the whole function, then again z minus 2 is going to cancelled out, so we are having the limit as 9 by 4. Now for f z equals to 0, the residue that we have to calculate it using the second formula, because it is a pole of order 2. So what is the formula for pole of order 2? 1 upon m minus 1 factorial, that is 2 minus 1 factorial, limit z tends to 0, d to the power 2 minus 1, dz to the power 2 minus 1, z minus 0 whole square into the whole function. Okay, so now z square and z square are going to cancelled out from here, and we have to take the single derivative. D to the power 2 minus 1 means d dz, so d dz of z plus 1 whole square divided by z minus 1, z minus 2. So applying u upon v rule, we are having the derivative like this, and thereafter we have to substitute the limit z tends to 0. So after substituting limit z tends to 0, the result is coming 7 by 4. Since all these 3 poles are inside the circle, therefore using the Cauchy's residue theorem, what we can conclude from here, the value of the integration is going to be 2 pi I into sum of all the residues. So after adding all these 3 terms, the result is going to be 0, so the value of the integration is also becoming 0. Now we come to the next part, next question, example number 3. We have to find out the value of the integration over c z upon z square plus 1 dz, where c is the circle, mod of z minus I equals to 2. So here the denominator z square plus 1, it can be factorized into 2 parts, z plus I, z minus I. So if I put z equal to I or minus I, the denominator is going to be 0 only. Both the powers of the factors are exactly equals to 1, so z equals to I and minus I, both are basically the simple poles. Now we have to draw the circle. So here if we draw the circle, we can see z equal to I is lies in the imaginary axis, so it will go up to 2 radius, so it will go up to plus 3i and it will go up to minus I. So basically the plus I and minus I, both the points are lying within this circle, within this region. Therefore we have to calculate the residue at both the points. Since both are the simple poles, so we have to apply the simple pole formula, that is formula number 1. So after doing this, we are having the residue at z equals to I is 1 by 2, residue at z equal to minus I is another 1 by 2. So using the Cauchy's residue theorem, we are having the value of the integration as a 2 pi I into sum of all the residues. So the result is going to be plus 2 pi I only. Now let us come to the next example, that is find the value of the integration cos pi z by z minus 1 z minus 2 dz, where the circle is about z minus 1 by 2 equals to 1. So whenever I am showing all the examples, you have understood that the problem actually can be solved whenever we can be able to understand what is the poles and whether the poles are lying inside the circle or outside the circle. So if it lies inside the circle, we have to calculate the residue. If it is lying outside the circle, no need to calculate the residue, because the value of the integration for that particular point is going to be 0 using the Cauchy's theorem. So here if we just focus on the circle which is centered at the point 1 by 2 and radius 1, so it is the center at 1 by 2. If radius is 1, then it will go up to 3 by 2 and it will go up to minus 1 by 2 on this point. But in this region, only one point of this singularity will lie, that is z equal to 1, and z equal to 2 lies outside the circle. Therefore no need to calculate the residue at z equal to 2. Since z equal to 1 is a simple pole, so we have to again apply the same formula for the simple pole, and we have calculated the residue result is coming 1. So the value of the integration by Cauchy's residue theorem is going to be 2 pi I into 1. This is equals to 2 pi I. Next let us come to another example. So we have to evaluate integration over c z minus 1 upon z square plus 2z plus 5. So here see that the denominator is not given in the factorized form, so we have to make the factorization. So we are applying the Sridhar-Acharya formula to find out the values of z, for which z square plus 2z plus 5 is going to be 0. The result is giving us minus 1 plus minus 2i. So the two poles are there, minus 1 plus 2i and minus 1 minus 2i. These two are both the simple poles, because if we just factorize it, then using the Sridhar-Acharya formula we are having z minus 1 divided by z minus 1 plus 2i. This is going to be one factor. Another factor is z minus 1 minus 2i. This is going to be the another factor. So this is the form of this function basically after doing the factorization part. Now we are having the two circles here. First circle is mod z equals to 1. So mod z equals to 1, center at 0, it will go to plus 1, here it will go to minus 1. So definitely this both the points are outside the circle. So it will go in the imaginary side plus I, and it will go here in the minus I. So definitely all the 2 points are outside the circle. So hence we can deduct from here that the value of the integration is going to be 0 for mod z equals to 1 using Cauchy's theorem. No need to apply the residue theorem. Now if we go to the second one, that is very interesting one, mod of z plus 1 plus I, this is equals to 2. So here if we just write down the structure of the circle, so it is mod of z minus 1 minus z minus minus 1 minus I equals to 2. So the center of the circle is at the point minus 1 minus I. So here it is the minus 1 minus I point, and the radius is 2, so it will go up to here minus 1, then it will go up to minus 1 plus I, and here it will go up to minus 1 minus 2i, and here also minus 1 minus 3i, right? So this point minus 1 minus 2i will lie inside the circle, but plus 1 plus 2i, that will go outside the circle, right? Therefore only we have to calculate the residue at the point minus 1 minus 2i. So the value of the residue is coming 1 plus I upon 2i, because it is a simple pole, so we have used the simple pole formula, and by using the Cauchy's residue the result is coming 2 pi I into this, so pi into 1 plus I. Let us come to the last example. So here we have taken e power 3z by z minus 1 whole to the power 4, and the circle is given as mod z equals to 2. So definitely now all of you have understood that at z equal to 1 the singularity exists and it is a pole of order 4 because power is given as 4, and z equal to 1 definitely it lies inside the circle, but it is a pole of order 4, so we have to apply the second formula for finding the residue. So by second formula it is 1 by 4 minus 1 factorial, that is m minus 1 factorial, limit z tends to 1, d to the power m minus 1, so it will be 3 and 3. Since it is a pole of order 4, so here it will become 3 and 3, 4 minus 1, z minus 1 whole to the power 4 into the whole function. So z minus 1 whole to the power 4 whole to the power 4 is going to cancelled out. We have to take the 3 times differentiation of the inside function e power 3z. So the result will come 27 e to the power 3z, 1 by 6, the limit z tends to 1. So the result is going to coming as 9 by 2 e cube, that is the residue. So by Cauchy's residue theorem we are having the final answer as 9 pi I e cube. So with this topic we are going to close. Thank you all.